We're moving past our introduction of some of the notation and some of the methods that we'll be using, and we're going to actually move into our first section of describing motion. The name for that is kinematics, and kinematics is just a fancy word for describing something's motion. So I have a couple charts here, and I'm just going to be discussing these here in this video. First thing I want to look at here is this top image. This could represent someone walking to school, for example, say a student walking from their house to school. And we're going to pretend that they're walking in a straight line from their house to school. They're not taking any turns. So what this image shows is, first of all, the time between successive dots is equal. Again, the time between each of these little dots is equal. But you notice that these dots have a different length between them, a different length of a vector between them. So if these are the same time between these dots, and we look here, we see this is an image of some position. Well, what can we say about this? So let's think about this. This is obviously showing some distance traveled, but if it's in a different amount of time, well, we see here this first, second, and third vector, they're the same length. So this student was traveling the same amount of distance in the same time. So we can say that they had the same velocity for these three vectors right here. They were traversing a certain distance, and it was equal for these first three moments in time. We then get to this next portion here, and again, keep in mind the time between these dots is the same. So even though this shortens, the time between these dots is the same. So what does that show us? Well, they've traveled less distance in the same amount of time, so they must be moving slower. And then we get to this next section here, and we see that these vectors are increasing in length. They're traveling a further distance in the same amount of time. And so it's useful to look at this type of dot diagram, but if we want to show that in a graph, well, we can use a position versus time graph. A position versus time, when we say position versus time, that means that position, this value here, this distance, is dependent on time. So time is the independent variable. So this graph shows us the same motion that's occurring in this top image here of the dot diagram. It's just represented in a new form. So now we're seeing here that time is on the x-axis, the horizontal axis, and position is on what we would generally consider to be the y-axis. And we can see at certain parts, this line gets steeper, and the exact values that are on this graph are given here by this table. So we see at time 0, position equals 0, so that's right here at the origin. At time equals 1, so this is right here, halfway between 0 and 2 on the time axis. We see position equals 60, and that looks to be about right. So this graph here is a mirror of this table, and this table is just the exact values that we found here on this dot diagram. So what can I say then about, let's just look at this portion right here between these two subsequent points of time equals 8 seconds to time equals 9 seconds. Well, that's the very last section here on this table, and it's the very last vector here on this dot diagram. And we said that the students started at a certain speed and they maintained that for 1, 2, 3 intervals of time, and then they slowed down. We can say that they slowed down because they're covering less distance in the same amount of time. Again, I've said this over and over, but it's very important to remember that the time between these two dots is the same. So we can see here that, well, they sped up quite a bit here at the end. Well, how's that indicated on this position versus time graph. How do we see that their speed has increased? Obviously, we see that we had some shallower angle, and then it flattened out a little bit, and then it got steeper. So, well, let's remember what our definition of velocity actually is. Velocity is defined as the change in position with respect to time. So the position changes between time equals 8 seconds and time equals 9 seconds. Clearly, the position is changing as well, because it goes from, if we look at our chart, 440 meters to 540 meters. Okay, well, that is a change in position. Look, position change, that's a delta x. And we can see here time change from 8 to 9. That is a delta t. So the slope of this line on the position versus time graph for this segment, the slope is the velocity. And I can represent that with an equation. Velocity equals delta x over delta t. Well, delta x equals x final minus x initial. Delta t equals t final minus t initial. And let's go back to the chart. Well, this 9 is the final time. This 540 meters is the final position. So I can plug that in over here. Final position of 540 meters. And the time is 9 seconds. And my initial time was 8 seconds. And my initial position was 440 meters. When I do the simple math there, 540 minus 440 is 100 meters over 1 second. And we can then look at this and say, well, what is this? It is the velocity. It is the velocity. So the velocity for this period of time, v equals 100 meters per second. So we gathered all that, and we can gather all that just from this graph. I just had a bunch of different ways to represent it. The first way I represented it is by showing this dot diagram that, hey, something is changing here with these vectors. Something is clearly changing. The lengths are changing. And what does that translate to when we look at a graph? One final image that I'll show then is we can make a continuous graph of the position versus time graph that we have above here. So this is the same graph. All we've done is we've smoothed out, we've connected all of the points. And this shows the student's position at all instants of time. Hopefully that makes sense. When you're traveling, you don't hop from one dot to the next. While you're in your car or while you're walking, it's continuous. Like, your change in position is continuous. You're always located somewhere. You're not just hopping or warping from one position to another. But these points are what we've sampled from this dot diagram. And this table gives us those exact values. So just to recap, first we looked here at this position versus time graph. This shows us, obviously, this student has positive velocity. It's continuous this entire way, even if it slows down and we see smaller little vectors here in this segment. So because the person has positive velocity, they're going in the same direction the entire time. So we have positive displacement for the entire time. We start at displacement equals 0 to displacement equals 540, as indicated by the chart. We can then connect all those lines and we can see this continuous curve that describes the student's motion. Finally, when we look at the slope of this graph, that actually gives us the velocity of the student when we look at a different segment. In this case, we looked at the end segment and we determined that the velocity is 100 meters per second.